Hello everybody, my name is Maren Erven and I'm happy to be here today to speak to you about our research in the field of additive manufacturing with steel. I'm a research assistant at the Institute of Steel Construction and Material Mechanics under the direction of Professor Lange at the Technical University of Darmstadt in Germany. And my presentation today has the title 3D Printing with Steel of a Bolted Connection. Now let me give you a short overview about what you will hear in the next 12 minutes. And I guess the question which is the most important is how is it possible to 3D print with steel? And I will explain that to you in just some seconds. But then there's of course the question of what we should print with steel in the construction industry. And in this presentation I focus on hub plates. After that I will shortly explain what is topology optimization and how I used it to find a structure to print. And surely we print that structure and I will show you how in the second half of the presentation. And also we tested some of the printed structures and with the results I want to end the presentation. Now begin with the most interesting question. How could we print with steel? And the AM process we use is the wire arc additive manufacturing, or WAM, or just WAM. What is actually just normal gas shielded metal arc welding, but unlike in common manufacturing we don't connect two pieces, we use it to create the second piece itself. And here you can see an animation of the process. The welding robot works with normal gas shielded metal arc welding, and the wire electrode is the printing material and the structure builds up weld by weld. With this process we can achieve deposition rates up to 5 kg or even more if we use multi-wire feeding systems. And that's pretty fast compared to other 3D printing. For example, powder bed processes, they can produce up to 1 kg in an hour. So that's one advantage, but the other advantage is that arc welding is a process well known in the construction industry, so the implementation wouldn't be that difficult. As we all know, in steel construction, bolted head plates are a common connection because it's quite easy to produce. But however, because of the offset of the bolts, the plate is subjected to bending, which makes it less economical. A sufficient plate thickness is required to transfer this bending moment. And furthermore, there are some areas like the middle part of the plate which have very little or no load at all. Maybe with 3D printing we can find a structure which uses the material more efficiently. And therefore, here a short throw-in for topology optimization, which is one kind of structural optimization. Here, a structure is optimized by inserting holes where the material is not needed. So we have our structural problem right here above me. And for a given mass, like 50% of the original one, the algorithm finds the structure with a minimum compliance. But the state of the art, you don't know yet what is the payload of this optimized structure, so you have to do a new analysis in addition to get that payload and see if it's a valuable design. As I said, that presentation focused on head plate. Let me be a bit more specific. Especially the tensile zone of beam slice was evaluated, and a simplification and possible shear force was neglected. The FE model was limited to the T-stub area of the head plate, so just the effective zone was considered, and instead of modeling the bolts, they were represented by bearings. Compared to traditional manufacturing, additive manufacturing allows new, more complicated, but actually more efficient geometries, and therefore the thickness of the design space in blue was increased compared to that of the original head plate to enable maybe a more effective load transmission. But by increasing the height, it should be noted that there must be a sufficient space for tighten the bolts for the assembly, so there was a cylinder left out in the design space. And here you can, in this diagram, you can see in red the line for the ultimate load of the conventional T-stub, and the blue line shows the ultimate load of the topology optimized structures. And when comparing the optimized structures with the original head plate, it can be seen that there are two angles formed, and with that there was with that rearrangement of mass, the mode of action changes, so like a truss, and it almost doubles the load bearing capacity for the same load, that for the 100%, and with only 40% of the original mass, the same load bearing capacity can be achieved. So in the future, a head plate could be maybe look like that, and the assembly is just as before. But the connection shouldn't just work for beam slices. You can also think of a beam column connection. Yeah, until now I just shown you some simulation results. Let's check if the WAM is an applicable process. And to justify that, we make a printing strategy, but as WAM is a quite young process, there were no sets of parameters available, like there are for plastic printers. So especially for voluminous structure, we have to think a bit more, because for one welding seam, there are at least the parameters, the travel speed and the wire feed speed influence the behavior and the geometry. But for voluminous structures, there's also the distance between each weld, which influence the outcoming structure. And this influence is shown on the left. If the distance d is equal to the width, then two separated lines will form. So it's easy to see that the distance should be smaller than the width of one weld. However, if the distance d is too small, the overlapping will lead to an increased height. And even if the seams overlap each other, like in the middle, there's maybe still a valley between the two welds. So for our printing, we changed the printing path direction for every layer. So it was rotated by 90 degrees. You can see it here exemplary for the layer 7 and layer 8. According to these starting points, there was a printing setup developed, and we had 9 specimens with different parameters. In the end, in general, it could be stated that the final contour proximity was actually equivalent, but the best result was achieved by specimen 3, which is in the right corner of the picture. And here the individual layers show a rather closed surface, and the height of the specimen was in accordance with the design geometry. Using these parameters for specimen 3, we printed further 2 specimens, and here it was checked whether it is possible to print directly to the edge of the base plate, because we need that for the real printing to the beam. If you want to assemble it, then you need to print to the edge. And also the distance between the 2 specimens was choosing according to the original distance, to check if there's any heat influence from one body to the other. But there were no negative effects observed. And here's a video how these T-stubs were manufactured. Firstly, there you can see the real-time printing. Later, it's a bit speed up, because the printing took 2 hours, including the cooling time, but yeah, I have just 12 minutes to speak. Now it's speeded up. And now you can see the rotation of the printing path direction. And the end. Yeah, in addition to the external inspection, some specimens were also cut to see maybe possible voids by eye, but there were no voids observed. For the production of the specimen, what you can maybe see, the bolt hole were not considered, so it had to be drilled afterwards. When we wanted to assemble 2 of them, then it occurred that the welding seams protruded into the area provided for tightening, so the intended wrench didn't fit. So for future designs, a certain distance for inaccuracy of the printing process should be included into the optimization. So the cylinder lift out should be a bit bigger. Besides the visual examination, a first evaluation of the load-bearing capacity was made on 3 specimens. Yeah, it has to be highlighted that the specimens were an outcome of the test of series for finding the right manufacturing study. And so we have just half of the T-stub and also a very thin base plate. And yeah, what you can see here is that the load introduction was eccentric. So the specimen rotates and the bolt receives tension and bending, but in all 3 cases the very thin base plate failed at the point where the load was introduced to the printed specimen. So it can be stated that the printed specimen can transmit at least 160 kilonewton, which is more than half of the half T-stub. So yeah, the printed steel works, but we can't really say what's the bearing load of it. Now let me sum up what you heard in the last minutes. Yeah, with WOW we found a process that can print steel, and it opens up new possibility for the designs of connections. You saw it at the T-stub. It really looks different. Yeah, but still, for head plates, the shear forces in a compression zone has to be investigated, and yeah, also the direct printing to the beam. For voluminous structures, there's still parameters have to be found, but yeah, the structural behavior of the printed steel can be evaluated as good, especially for static loads. Sure, for really the implementation in the steel construction, we need standards. So yeah, they have to be done a bit into that. Yeah, and now I want really like to thank you very much for allowing me to speak to you here and for your attention. And I'm curious to see and to hear if there are any questions or comments from you. Thank you.